Welcome back to another part 3 of this natural language processing lecture. So in this lecture we will be talking about word representation methods that are slightly more modern than the ones that we saw previously with bag of words and TF-IDF. In this lecture we will focus on the Word2vec representation. So the basic idea behind this representation is that given a word occurring in a document, we want to predict the words surrounding words, so the other words that are appearing around it in the document. So these surrounding words are also known as the word's context. So we start by embedding all the words using the bag of words approach, just like we saw previously, associate them with a bunch of one-hot vectors. So all the words will be associated to a one-hot vector with a bunch of zeros and a single one. We then fit two matrices. So this is the difference with this Word2vec representation. Two matrices, mn-code and md-code. So mn-code is a v, D matrix, and md-code is a d, v matrix. So here v is the size of our vocabulary, which we saw is just the number of unique words occurring in our corpus. And D is the embedding size. So this will be the resulting size of the representation, or resulting number of dimensions that our representation of the words will have. So we can set this size, this embedding size, to be whatever we want, but usually it's set somewhere around 50 to 300. So the idea here is that we want, when we input a word, W, and we encode it and decode it using these two matrices, then we want the result to be equal to W's surrounding words. So here we usually take surrounding words to mean words that are at most 2 hops away, by which I mean the neighbors of the word and the neighbors' neighbors of the word. So if we start with this example, I really liked Ali Smith's new book from before. If we focus on the word liked, we start by encoding the word liked in a one-hot fashion, like this bag of words representation. So this will be a bunch of zeros and a single one. We then pass it through the encode matrix, resulting in an embedding layer of dimension D, this embedding dimension that we chose, and then run it through md-code to blow it back up to the size of our vocabulary once again. So the resulting vector here will be a vector full of probabilities, and what we want is that the neighboring words, so in this case that would be I, really, Ali, and Smiths, if we can look at the example up here in the top left, then these neighboring words, we want those to have a high probability in this output layer. So really, what we're doing after encode decode to convert this to a vector of probabilities, to be able to do this, we apply the softmax function, which you have seen previously, which just converts all these numbers, which could be any numbers, to probabilities between 0 and 1, so that all of the probabilities in this vector will add up to 1. So to create embeddings of sentences or of documents, we need to aggregate the individual word embeddings. So we need some operation which somehow merges the individual word embeddings. We can take the mean, that's very common, but sometimes taking the maximum can be more sensible. So I'd like you to just ponder over this for a few seconds. Just what would the difference between using the mean and the max be here? So there can be many differences between using the mean and max. One answer or one difference between the two is that the max would emphasize the use of certain words. Say if we have a word like hate in the sentence, then the maximum would spit out the value roughly the rough value corresponding to hate, where the mean would also take all the surrounding words into account. Also, if we use the mean and we have a very long sentence, then just by the way the mean works, we would degrade the representation the longer it gets. So if there's a bunch of fluff at the end of the document, this would make important words like hate less impactful, so to speak. Where if we're using the max, then hate, if it remains the max when we have longer sentences, it doesn't matter how long the sentence is, it would just spit out that representation. Okay, so with Word2vec, we actually do obtain this picture that I showed you in the very beginning, in the first part of the lecture, where if we have a representation trained in this manner, we do get this relationship between king, queen, man, and woman that we saw before. So going back to the checklist, we still do scale words according to their rarity, since we are basing our embeddings upon the context. So if we look at the word the will appear in lots of different contexts, which means that the probabilities in the last layer, the final layer that we saw, will be very minuscule because it has to sum up to 1. But if it's a very rare word, then that tends to be only associated with fewer neighboring words, so their probabilities will be larger. So it does scale these words according to their rarity. This representation here captures correlations between words, so a correlation between the words woman and she, for instance. There are still some downsides with the Word2vec representation. It still cannot handle new words that were not present in the training data, because we're still using the bag of words representation to begin with. And secondly, the representation is still static. Even though we are taking context into account, like the surrounding words, we are still associating apple the fruit to the same embedding as Apple the company. So for a classification task, it does sometimes perform better than TF-IDF representations, but there is no clear winner here. There are some tasks where TF-IDF is superior, and there are some where Word2vec is superior. So the second kind of variation of Word2vec that I would like to discuss here is what is called FastText. So this is a variation of the Word2vec representation, which solves another one of these issues in our checklist. So this is the out of vocabulary issue. So the only difference between the FastText embedding and the Word2vec embedding is that rather than splitting a document by words and just working with words as entities, like atomic entities, we split up those words in character n-grams. So by that I mean we take a word, like the word really here. We then look at triples of characters appearing in the word. So we can think of this as a sliding window of 3 characters that are just sliding 1 character at a time towards the end of the word. We also, this is a minor detail, but we also assign some special characters to mark the beginning and end of the word, so that this representation can know that this re here is a special re because it's the beginning of a word, compared to just re appearing in, say, are. Okay. So a common choice, so we saw here that I was taking trigrams, like n was equal to 3, and that is very common and is usually the standard. We can, however, also use bigrams to use 2 characters at a time. can be more powerful, but it requires more compute because we will suddenly just have more n-grams to deal with. So it's a bit slower. So to compute a fast text representation, we start by splitting it into words, like normal. Then we train the algorithm exactly like Word2vec that we just saw. We train these mencode, mdecode matrices. But the resulting word embeddings in the middle are now the normalized sum of the embeddings of the n-grams in the word. So we take a word, split it up into all the individual n-grams, embed every one of them, sum them up, and normalize the sum, and that would be the middle layer of our neural network. And then again, we blow it back up, and we want to predict the neighboring words. So that's when we're training. When we want to apply this at inference, so say we actually have a document, we have a trained fast text model. What this fast text model is doing is that, again, it's splitting the words in the document into n-grams, and again it returns the normalized sum of the n-gram embeddings, exactly like what's going on in the middle layer during training. So yes, it's more compute because we have to essentially embed a lot more things compared to only the words, but this also means that we do take care of the outer vocabulary question, because a word would consist of individual chunks or n-grams that we hopefully have seen before. There is, of course, the chance of a word having a character trigram, say, which we have not seen before, but that's way more unlikely than seeing a word that we haven't seen before. So this satisfies, again, the first 2 points, just like Word2vec, but aside from that, it can also now handle new words that were not present in the training data. It still has the last problem of representation being static, that apple the fruit is still equal to apple the company. Performance is quite similar to Word2vec, but because of this ability to deal with out-of-vocabulary words, it's way more robust compared to that, like when we want to apply this model in practice in the real world. So conclusion, Word2vec and FastText are two newer types of word representations. Again, the primary feature is that they can take correlation between words into account, which we saw with, say, king and queen and man and woman. FastText is an extension of Word2vec, which can also handle this out-of-vocabulary problem. And these vectors are, of course, good for visualization, but they are not necessarily clear winners over TF-IDF vectors for classification. That depends on the task at hand. And lastly, here are some references where Chapter 6.8 in Juravsky and Martin is an introduction to Word2vec with some examples. We also have the GenSim documentation. So this is the GenSim Python library documentation of Word2vec and FastText. And on the right, we have the two original papers introducing Word2vec from 2013 and FastText in 2016. And that's it for this part.